So, continuing with plate preparation, we had been talking about mill scale, the ill effects of mill scale if we do not remove them, and there we saw that some methods have should be employed such that this mill scale is effectively removed. Some of the methods which we have talked about appears to be not very efficient, not very effective, because we talked about natural method, that is naturally the mill scale it gets descaled, rather it peels off. So, thereby it's difficult to ensure 100% removal, and also it may lead to local corrosions in the plate. Next method we talked about is the flame treatment. Flame treatment is nothing but you take advantage of the difference in the thermal expansion of coefficient of the plate and that of the mill scale. So, if you subject it to a certain kind of controlled heating, if it is subjected to a controlled heating, say for example, you take a gas flame, a gas burner and heat it, then it is expected that the mill scale will peel off, because it expands more compared to that of the steel, and thereby it will get loosened and it will peel off. So, that is a somewhat better method compared to the your natural process, because it is much more faster. But again the method is not very effective, I would say, because here it involves controlled heating. Now, controlled heating means what? That means you will have to ensure that you do not exceed a certain level of temperature in the plate, because if you do that, the plate gets subjected to a probably undesirable thermal cycle. You are heating it means what? You are subjecting the plate to a thermal cycle. It is getting heated up and then cooling down. So, we know if the temperature the plate is attaining that gets beyond certain critical temperatures, there can be damage of the metallurgical properties. That means so called microstructure may get affected, and at the same time it may cause deformation of the plates. We have already straightened the plates, passing it through roller. We have reduced the tried to eliminate the residual stresses, if any, but this thermal process, apart from damaging the microstructure, means affecting its metallurgical aspects, may also cause some thermal stresses to develop in the plate, leading to deformation or leading to locked in stresses, means formation of residual stresses.
So, can't we do the other way around, means flame treat it first and then go for straightening process?
Well, that is possible, that is definitely possible, but in the process what is happening, if we assume that we are using this method, then we can do the straightening method later. That is possible, definitely. But here again the question remains, well, thereby we can sort out the problem of residual stress, if any, which is forming, or the plate getting deformed, that can be sorted out. But the problem remains that it is difficult to ensure full removal of the mill scale, 100% removal of the mill scale. That problem remains. So, once again we see that this method is also not a very effective method as such. Next method which we talked about was some kind of mechanical means, that means by wire brushing. By wire brushing, simple manual brushing won't help much, because the bondage is very strong. So, it needs to be some kind of pneumatic brushing or power, I mean the entire brushing mechanical operation has to be done under power. Well, this is somewhat little better effective wise, better compared to the previous methods, but you can well imagine how hazardous the process would be. Whoever, if it has to be applied manually, then not only it will cause lot of noise pollution, also, or other words, not only it will cause loss of dust pollution, it will also cause noise pollution. Means the operator will be subjected to a very, very bad environment. It will generate tremendous amount of dust, along with that tremendous amount of noise, high decibel noise. But well, all these we are talking about, that these are some of the means. At least we can remove some part of the mill scale if we do not have anything better. Till now we have seen that all these are not very not very capital intensive processes. It's rather being done with very simple tools, hand operated tools. The heating is by a gas flame. So as it is, you will be having at least oxyacetylene flame or oxyacetylene gas for cutting requirement. So with that it can be heated. You will need different kinds of nozzles, of course. Mechanical brushing, okay, some pneumatic brushes can be used, but still again the problem remains that they are not effective. Then comes, so another, this gives us another aspect, that this process of mill scale removal has to be made automated if you want to make the process faster, as well as make it more, if we say, environment friendly. It has to be made in such a fashion that it does not lead to dust pollution, because dust pollution is a very bad, I mean it's a terrible hazard for the workers. You cannot afford to have that. And second is the noise has to be eliminated. That means whatever method we use, it has to be some kind of automated method, Then automatically what is happening? The worker is not getting involved. He is not subjected to that dusty and noisy environment. Right? So there we came to the method of short blasting. It is also another mechanical method. So we call it short blasting. The short blasting, if you see schematically, it is something like this. As you can see, that here the plate enters from one side of the say this is schematic description of the chamber, short blasting chamber, right. Here the plate enters the chamber, moving over the roller conveyors. These green small circles, they indicate the roller conveyor. So after the plate is coming out from the straightening machine on the roller, straightway it is put on the the same conveyor line goes. So it enters the short blasting chamber. So by putting it within a chamber, what you can see is that you have a suitable sound insulated chamber, suitably covered, right. So automatically what is happening, whatever is happening inside, it does not sort of affect the environment outside. So what is happening inside? As the name suggests, short blasting. That means the plates are blasted with shorts, steel shorts, right, steel shorts. So schematically I have shown it here with these red arrows, that means you can have 4 jets, right, blasting the shorts over the entire breadth of the plate. Here we have shown a cross section. So this, they are the over the entire breadth of the plate, right. Suppose the plate breadth is like this. Over the entire breadth, you can have the, there will be a suitable mechanism of shooting this steel shorts over the plate surface from both sides. So what is happening? The plate keeps moving, and it is subjected to a high energy sort of blasting of steel shorts. In the process, what happens? What are these steel shorts? They are small steel, something equivalent to that of, if you think of small ball bearings, if you break them, right. So such small particles So, it will have some sharp edges, right. So, as it is implode on the plate surface, what will happen? It will hit the plate and will get reflected back, right. It will hit the plate and it will get reflected back. In the process, what it will do? It will chip off the part of the material on the surface. Right. So, thereby as the plate keeps moving from both sides, I am blasting the surface on the top as well as at the bottom. So, the shots are coming, hitting it and getting reflected out. While it is going, each particle is taking out a small chip of the plate surface material, and the surface material is the mill scale. Thereby, it is cleaning it. Now, the question comes that how do I ensure that it is really taking up the 100% of the mill scale? Because it can be something like this. I just scrape it out. Say there is 10 micron thickness layer is there. I scrape only 5 micron, 5 remains. Or I scrape in such a fashion that I scrape off 15 micron. So, not only the mill scale goes, but also the steel material goes. So, these are again the so called drawbacks or so called aspects which are to be looked into while setting the parameters of the machine. So, what will be the parameters? Parameters would be, it will depend on how much energy I must impart in those sorts such that it should be able to chip off the material. At the same time, I do not impart too much energy that it chips off to a greater depth, right. So, thereby parameters, if we try to quantify, there will be velocity of these shots. These shots are generally, they are generally it is done by there is a impeller kind of thing. So, from a again, well, if we schematically it is somewhat like this. You have a if we just think in schematic term, say this is a hopper where the shots are kept, right. It falls on this impeller. Here what I have tried to draw is a kind of a impeller having blades like this. It is rotating at a certain RPM. So, what will happen? It will impart a energy in the shots, and when it comes the exit, it goes out at a high velocity. So, at what velocity it will go out will depend on the RPM of this impeller, right. So, eventually we are interested on the velocity of exit of the particle, its mass, its size. In fact, these are the 3 basic parameters which are interested in, because this will give me with what energy it is coming and hitting the plate, and depending on this energy it will do the job. Means either it will sort of chip off a part of the mill scale, or chip off exactly as you want, or chip off more, right. So, thereby we see that. So, this is just a schematic representation of how it works. So, we will have parameters like velocity and another parameter of course, like at what angle it is being shot at the plate surface. This angle theta, that means at what angle you are blasting it. Here the way I have shown, we have as if 4 sets of shot blasting unit, one from this side top and bottom, another from the other side top and bottom, such that to ensure full breadth of the plate, both top and bottom side perfectly removed. So, another important parameter is the angle, at what angle you are shooting it on the plate, and definitely the size and the weight of the particles, the shot of the shots. So, these are your so called parameters are to be controlled such that we ensure 100% removal of the mill scale.
So these reflected shots will not form in.
Yes. So, now as far as the process is concerned, as it is done, then all your shots will get accumulated here, right. I mean which are getting reflected, that means shots along with the dust, along with the mill scale powder, because it will be in a powdery form, will get accumulated at the bottom. So, we will have a mechanism of filtering it out and recycling back the shots. So, the shots are recycled. Obviously, in the process some of the shots will lose its character. Character means basically will become smaller in size, thereby lesser in weight. That means they will also break, they will get worn out. So, well, time to time some kind of you will have to so called whatever is getting lost, replace them, replenishment is to be done, right. So, here we see that the entire process is carried out within a chamber, and also the feeding of the plate material as well as taking out of the plate material, everything is automated. By automated, here automation is done through roller conveyor. That means after the straightening operation, plate straightaway moves into the chamber. Chamber is closed, right. Only opening you have is where from the plate is entering and the edge where the plate is coming out. That opening is also covered by a flexible rubber like material, which is a flexible material. So, thereby I mean the plate can push the rubber material and goes out, but physical closing is there. So, this dust, I mean very little, I mean one can say hardly any dust comes out from the chamber, and it is well acoustically insulated. So, you also do not hear a big noise, otherwise it is a very noisy operation, right. So, entire noise is also confined in the chamber, as well as the dust is also confined. So, thereby you make the process, I mean so to say, very much environment friendly. So, that is what is the shot blasting. So, here we see that the rate of operation, how fast we can do it, that will depend on how fast we can move the plate. That will again depend on, if we move the plate very fast, then probably we may land up not removing the entire amount. We move it very slow, we may land up chipping off the plate, right. So, there is another parameter, that is plate speed or plate feed speed. At what speed the plate is being fed, right. So, that also becomes another parameter which is to be controlled for proper operation of this, for proper shot blasting operation. And also this parameter determines your productivity, because as far as the end user is concerned, he is not bothered at what angle or velocity or size, weight, he is only bothered about at what speed I can move the plate, because that is my goal, that I want to have this much of productivity. So, productivity here is given in terms of productivity of this operation is given in terms of meter square per hour. Again, speed is not the exact productivity, because to quantify I should be able to say that so many meter square of plate has been mill scaled, I mean has been descaled or has been prepared. So, productivity comes in terms of meter square per hour, how many meter square per hour it can sort of clean. So, the more or less this varies somewhere within 100 to 200 meter square per hour. 100 to 200 means depending on the kind of machine, etc. This may vary between 100 to 200, and also depending on the plate thickness, also this will vary, right. Though plate thickness is not a direct parameter which is to be controlled, that is being given as a sort of I mean, that depends on what all plates you have, and you will have to clean it, right. But that has a indirect effect on these parameters, or rather has a direct effect on these parameters. Can you tell me why? How plate thickness comes into picture? Because the whole operation you have seen here, what is coming into picture is essentially the plate breadth, because depending on the breadth I have to make the machine arrangement such that I can cover the entire breadth. Okay, that is done because we know the breadths are standard. Here we won't be doing that, this time I put 500 millimeter plate and next time I put 3 meter plate. No, standard plate sizes are either 3 meter wide or 2 meter wide. Generally these are the two standards followed, and shot blasting we are doing right at the beginning. That means we have the full size rectangular plates. We have not done any cutting operation yet. Okay. So that is done, and based on that plate breadth and the speed, I have the productivity meter square per hour. It's nothing but basically breadth into the speed of movement, right. Now, what role thickness may have here, or in other words, if I ask, we have seen the previous methods of natural, thermal, etc. There are drawbacks. What you can think is the drawback here? As of now, it works. It looks quite a effective method, and I can tell you that once we set this parameter properly, right, then we get the plate surface to our requirement. That means we can ensure 100% removal of mill scale, also can ensure proper surface smoothness, and we need generally a smoothness parameter of SA 2.5. That grade of smoothness, surface smoothness is possible, we can get, and the process is automated. So, your operation is very convenient, it's environment friendly, the shots are recyclable, right. So, everything is good. What is bad about it? Because there ought to be something negative. There cannot be anything in this world which is always 100% good. Has to be something bad. So, tell me, what could be bad here, or what could give us trouble, what could give us problem? Yes, time is, you say, no, here also if you talk about time, previous all three methods what we have seen, it is much more efficient. Here production rate is quite high. Like for example, natural method production rate would have been fantastic, because 6 months you keep the plate, right. Flame heating, okay, it cuts down very much, but there are other things that quality of the end product may not be as good. Wire brushing, well, again, it's manual you are doing, so productivity will be less, speed of operation would be less, and also hazardous. Here speed of operation is quite fast. That means it has something to do with thickness, that is number one. It has something to do with the surface hardening of the plate, because what is happening when you are blasting the plate with these shots, it is what operation it is we are hitting with a high energy particle, right. Yeah, I mean, yeah, there can be a possibility of that shots getting embedded, okay, that generally doesn't happen. The heat, well, it will generate some heat because of friction, but that will get dissipated, that will not affect. What will affect is that very process of impact, local plastification of the material is taking place, means locally the material stress is exceeding the yield point stress. It's something like what we call cold work, cold work. You take a hammer and hammer on the plate, apparently nothing happens. If you see the plate, nothing happens, but in that local area, what has happened is, by that solid, if you can hammer, what has happened is If you hammer really hard, then there will be a dent. Suppose the plate is lying on a flat surface. So, plate material will get depressed there. That means a permanent set will take place. That is visible. If you hit little less, that means less but just above the yield point stress, but not much of strain is taking place. So, nothing will be visible, but the material there has undergone a strain equivalent to that much, equivalent to the yield point stress, or in other words, if we see here, suppose this is my strain and the stress axis, your steel material has a stress strain characteristics somewhat like this. Somewhat like this, right? That means for till a certain stage it behaves elastically, that means follows Hooke's law. As you exceed that, there is a small hump there. If you forget that hump, exceed that yield point stress, then you have a kind of a flat valley. That flat valley, it is nothing but significance of that is as if under no additional load, the material keeps flowing. That means deformation continues, or in other words, under very delta increment of load, the material will deform. Or in other words, once the metal has yielded, we will say that it has lost its load carrying capacity, because under a very small increment of load, it will go on deforming. You can see the extent of deformation. Till such time your deformation was only this much. Only this much, right? And then as beyond sigma y, we have just we have increased the load little more, then my deformation increases so much, substantial, right? So, what happens? So, that is what is the significance of this, but again we see that it starts gaining strength, as if it is gaining strength. Means we have said that as the material reaches yield point stress, it does not have load carrying capacity, but in practicality, in real life, it will not have load carrying capacity for a certain stretch, for a certain level. Beyond that, again it will show strength. Means again you will need sufficient load so as to effect deformation. Like here we are needing sufficient load, sufficient stress level. Here also, then beyond sigma y, again you will have to increase the stress level such that you get some more additional deformation. When you relieve the stress, release the load, then what happens? Then material will come back to this state, elastic. This is called elastic unloading. That means this will be my permanent deformation. If I load up to this point, this will be my permanent deformation, right? Now, imagine a situation that you have loaded the material up to this point. It has showed some permanent deformation. Now, again you are subjecting the same material to some load. So, what will happen? How it will behave now? It will behave in this fashion. It will start operating from here. That means now it will behave elastically up to this point. So, now it will behave elastically up to this point. Its new yield point stress has become sigma y1, and then it no more has this value. Then again it will start gaining load. By gaining load, why you use that term? Because this can be seen in a universal testing machine, which is called UTM, where you subject a specimen to a tensile test. You slowly apply tensile test. So, what do you get? Load deflection curve. This is load deflection curve, because load divided by constant cross section is stress. Deflection is incremental deflection divided by the length. Gauge length is strain. So, gauge length is constant, area is constant. So, load deflection curve is nothing but sigma epsilon curve, stress strain curve. So, same thing will be visible, right. So, if I apply a tensile load to sigma y1 position, right, and then release the load, that means unload it. Then again I actuate the machine, again start applying load. What I will find next time, that it will behave elastically up to this point. It behaved elastically only up to this point originally. Once I have subjected to a cold work, there is a cold work. In the cold condition I am applying load. So, that is what is referred to as cold work. Subjected to a cold work to sigma 1 level, unloaded it, again I am loading it. So, it will behave up to sigma 1 as elastic, and then immediately again start gaining load. At this point, this is my ultimate stress, sigma ultimate. At this point, the necking starts, transverse cross section reduces, right. So, the curve apparently drops and breaks, snaps. Curve is dropping, it does not mean that the load is reducing. It is essentially what is happening is that since the cross section is reducing, right. Anyway, so what has happened? What has happened to the material because of the cold work?
Hardening, more elastic.
It has got hardened. First thing, it has got hardened because its elastic limit has increased. So, it has become a harder material. Harder material means brittle material. So, its ductility has reduced, and here I can see the ductility has reduced, because now it can suppose I load it up to only this, not to the ultimate point, but just below the ultimate point. So, what happens now? And I release the load. So, always unloading process is elastic, right. So, it will come back this much. So, now my deformation is only this much, or in other words, and this is my ultimate. So, here I can see my ductility has reduced. Originally, my ductility was this much, isn't it? If the plate would not have been subjected to the initial cold work, this initial cold work we did, we subjected to some tension and left it. Again, I am putting it under tension. If I have not have done that initial tensioning, I would have a total so called ductility this much. That means the material was capable of so much of deformation before its breaking, but now the material is only capable of this much of deformation. That means reserve plasticity reduces, right. So, because of cold work, it leads to hardening of the plate, right. Hardening of the plate means its tensile strength is increasing, means yield stress is increasing. So, it is becoming more harder, stronger, right. But in the process, what is happening? Its reserve plasticity is reducing. Reserve plasticity reduces. You understand, right? Why this is happening? Because this is my reserve plasticity, you see that valley This is a very peculiar property of steel material. It has a very quite a long that so called valley in the stress strain curve, which gives me reserve plasticity. Why it is important? Because I have to subject the plate. I mean that talks about ductility also, so that I can bend the plate, I can shape the plate. Not only that, in the event of failure, it will take lot of deformation before it fails. Like glass, it will suddenly break, you won't get any hint. But if it is a ductile material, glass is a brittle material. If it is a ductile material, then it will deform sufficiently and then it will fail. So, it will give you a lot of hints before failure. That means, you have some so called earlier signals, right, that the structure is deforming, means well, it is going beyond its limit. That is why it is termed as reserve plasticity. So, once cold work is subjected to a cold work, it leads to reduction in reserve plasticity. So, what is happening? That means, it cannot take much of deformation. So, if I subject the material to a deformation larger than this, it will fail, it will crack. Or in other words, that if you do an experiment, you have a steel plate, you go on hammering at the same location for quite a number of times, suddenly you will observe the plate has cracked there, surface has cracked, because every hammering, first hammering I have done this hardening, next hammering I am going beyond this. So, again it is becoming harder gradually, and you are exceeding the load. Every subsequent hammer, if I increase my intensity, magnitude of force, then after some time I will find that the cracks have developed in the plate, right. That means that surface has become brittle, it has cracked. Or you go on, you hammer for quite some time, then take the plate and try to give it a bent shape, make a bend, something it was like this, make like this, you will find it has cracked. So, that is what it is. That is one of the bad points of short blasting, because here you are hitting it with those shots. So, that is giving, that is working as at every small shots hitting at with a very high velocity, and with its weight, the kind of kinetic energy it has or kind of momentum it has, locally the stress level may be exceeding the yield stress. So, that is also another thing to be worked out, that it should not exceed yield stress. If it is below the yield stress, no problem. That means, the material has not been subjected to cold work. I have done a cold work on it, that means some stress level I have imparted, but if it is below the yield stress, it will come back to original, means plate's property has not changed, it has remained. Here the property has changed, it has become harder. So, there is also another aspect which has to be kept in mind while deciding on the velocity as well as the weight of those shots, because that combination will give you the stress developing at that small points, and those small points are very closely spaced. That means, the entire surface is subjected to that level of stress.
So, it may so happen that if we are considering for sigma y, that is the yield stress, it should not exceed, then chipping may not be properly done.
Yes, these are the problems. So, we will have to keep this in mind. These are two contradictory requirements. I would like lesser velocity, lesser weight, so that I remain safe. I am assured that it will not exceed the yield stress, but it may so happen if I do not do that, then it may not chip off. So, then again the question comes, the type of those shots, the size of the shots, the kind of shapes, the sharp edges, the angle, all these comes into play. So, what I mean to say is, these are the features, these are the factors involved. So, while designing the system, while deciding the parameters, one have to keep these things in mind. Though I am calling it short blasting, it will do the job perfectly, but whether it is leaving behind some damage to the plate, then again the purpose is half served, because following this all kinds of fabrication work will go on the plate. Plate will be bent and you find it has cracked. Hairline crack is coming because this hardening is taking place only on the surface. The plate thickness is there, only the surface is getting hardened. If you grind off the surface, then again it's fine, but that is not feasible. Yeah, that is not feasible. So that is actually one of the drawback of this process. And there is one more drawback based on similar things. What is that? That is on thickness. If the thickness is less, this kind of work being done, that may lead to stress level, not crushing, it will deform the plate. It will deform, it will tend to deform the plate. That means, if I put a say 4 millimeter thick plate, pass it through this, and this kind of, it will not sustain this kind of energy which is being imparted on the plate, and under that sort of blast of those shots, the plate may deform. So that is another aspect. That means, if it is thinner plate, then it may not be suitable for shot blasting operation to be done. It may not be able to do. So one will have to think whether we club 2-3 plates together and put it together and go on changing. Then again that defies some other principle. That means, if we club say 2 6 millimeter plates together, it becomes 12. So it is somewhat harder when they are impinging with the shots. It will not deform, but in the process what is happening? The internal parts are not so. So once it comes out, I have to take it back, recycle. Taking back recycle is easy to say, but how do you do that? Its process is automated, and it defies the basic principle of material handling. That means, the plate is tracking back altogether. Its flow is this, say from left to right, and it is going from right to left. These are certain general principles of material handling, that it should be designed such that it should not track back, metal should not move back. I mean, that's the kind of principle one should follow and accordingly design. Reason is simple, like you can well imagine, if I have to track back the plate and feed it again, it's not only time, it becomes very complicated issue. How do you make it flow like that? Because it's not a case of powder, or I mean the entire flow pattern changes, that the entire thing becomes very complicated. So, well, in other words, thinner plates, it's not preferable in shot blasting. Maybe there you go for sand blasting, but again the effectiveness may reduce and all that. So that is how we see that these are the well, so these are the mechanical aspects as far as the shot blasting is concerned. And now once shot blasting is done, so the plate as it is coming out of the chamber, we have a very bright shining surface. Bright shining surface means, because steel otherwise is a very shining material, absolutely shining bright material, it is not at all a dull material, right. So when it comes out from the chamber, it will give that shine. So from that shine you can make out whether it is conforming to SA 2.5 or SA 1 or SA 5, whatever. How that is done? A very simple process. There are so called small templates, small samples, pieces of pieces of paper which has the similar texture as that of steel surface, conforming to required SA. This is some Swedish standard, somehow that is universally followed, right. So what basically you do is, you just take that strip, place it on the steel surface, it should match perfectly. That means the texture of the surface, shot blasted surface, and the texture of the test strip should be identical. I mean, it won't be able to, almost you won't be able to say where it is lying, right? Then you know it has been done perfectly. So, that is another aspect here, that the so called quality assurance. That means, at every stage of production, this is, if I take this as a production station. So, on the left side I have my input, raw material input, on the right side is the finished material output. As far as this is concerned, here I have the finished material, that is shot blasted clean plate, and here I have the raw material, that is the plate with the milled scale. So, my once it undergoes this operation, I have a duty here to check whether the finished product, as far as this station is concerned, that is a finished product, whether it is conforming to the required quality or not. And that required quality is to check for its surface smoothness, to check for its full removal of the milled scale. Both these things are checked by taking a close look at the texture of the surface, right. So, this is done. Now, if I keep the plate like this for some time, what will happen? It will turn brown. Why brown? It will basically oxidize, the surface will oxidize, and as you know, the plate as it is coming out, when it will get a final coat of paint to protect it from corrosion and all that, it may be not only several months, it can be few years, because the entire shipbuilding process, it takes several months. The several months could be 10 months, 20 months, 30 months in that scale, right. And well, one of the means, and these plates will be eventually subjected to a very highly corrosive environment, eventually, right. Why? Because it will be either operating, it will be generally operating in sea environment, in ocean environment, and ocean environment is a highly corrosive one, right. So, to protect it from that corrosive environment, there are different schemes. One of the scheme is painting it with some kind of anti-corrosive paint, etc., but that will be done when the product is complete. Means, when you complete the hull, before delivery you give the final coat of paint, right. But till that time, what happens? You have to also protect it, because otherwise it will lie in the open atmosphere or whatever, exposed to the atmosphere will corrode. So, what is done is, it is immediately, in fact, once it comes out, it immediately enters a shot blast, a priming chamber, right. The plate is coming from the rolling machine, entering the shot blasting chamber. We are checking here that, yeah, it is fine, and it is just close by, physically close by. That means, in fact, what happens is, many a time it is under one housing. This entire setup can be under one housing even. Only thing, you have access at this point from outside to check the surface, and rest you need not see what is happening. So, it goes straight away, goes to the priming chamber. Priming chamber is again nothing but in the similar fashion. There we had been blasting the plate with shots. Here we will be spraying with paint, with a kind of a paint. The paint is generally used, is a zinc rich paint. A zinc rich paint is used for priming purpose. What is the function of this paint? What should be the characteristics? Primary characteristics is that it should be able to protect the plate at least for good several months before it gets its final coat of paint. So, that means the paint should remain on the surface, should not get washed out, should not get scratched off or whatever. That is number one. That means it should be able to protect the plate for that minimum required period, and that minimum required period could be several months, right. That is number one. Number two, well, since after these operations the plate will be subjected to all kind of bending, cutting, welding operations. So, this paint should not come in way of those operations. That means, it should not adversely affect cutting operation, neither it should adversely affect welding operation, right, because cutting operation will be either oxide steel and flame cutting, or it can be plasma cutting, or it can be laser cutting. So, none of these in none of these methods this paint should interfere negatively. Next is welding. Welding also, that it should not interfere, that means it should not cause contamination to the weld deposit. Like if I use a wrong kind of paint, the priming paint, my weld will become porous, there will be a lot of porosity in the weld. Why? Wrong kind of paint means a kind of say synthetic enamel paint I use, it will do all the purpose of protecting and everything, but when it will burn under the heat of welding, generate enough fumes which may get trapped and forms porosity in the weld. That means, it will produce a defective weld. So, it should not be adversely affecting the weldment. There is the next requirement. And the final requirement is that it should form a good base material for subsequent coat of paints, because this will remain over which you will do the painting. You are not going to remove it. Over this only you may, at times what people they do is some kind of sand blasting they do, just to clean the surface. The purpose is not to fully remove this zinc rich paint, no, because this is a good coating. Why zinc rich? Because zinc here acts as sacrificial anode. It acts as sacrificial anode. That means, if any corrosion takes place, the paint will corrode, the zinc particles will corrode within the paint emulsion, and the steel will be protected. So, these are that is what is the priming operation. Followed by that is drying. There is another chamber here, nothing but nozzles blasting hot air, drying chamber blasting hot air. Why? Because after the priming, well, the paint is still wet, so you cannot take it out, your paint will get spoiled. Though this priming paint should be of such quality that it dries up fast, but still it takes some time. To enhance that drying process, is subjected to a drying chamber, where you expose the plate to a hot air blast, right, and your plate is dry. So, you see the entire plate preparation in this method of short blasting, it just enters at one end, comes out from the other end, finished plate. That means, here you have the raw plate with the mill scale, here you have the finished plate with properly primed surface, right, clean primed surface, ready for next operations. Okay. So, that is how we see is quite a effective and possibly quite a efficient method of mill scale removal. Okay. So, we stop here today. Next we will see chemical dressing.